now we are going to discuss about time division multiplexing. Or it is also called as TDM. Okay. Now this time division multiplexing is quite similar to the frequency division multiplexing what we have discussed in the earlier class, in which n number of modulating signals provided with a different sort of carrier are modulated, and then it is fed into a common channel and it is traveled throughout a particular distance. So in that, what we have done, multiplex means combining the n number of signals and forming a single signal, and the single bandwidth in which n number of informations are going to be placed without any sort of interference. If there is an interference, means multiplexing doesn't come across the technique through which the signals can be decoded. Okay, the multiplexing means combining the signals, combining the n number of signals and forming a single signal in a particular manner in which a particular signal will have n number of frequency component, n number of modulated component, and it is delivered in a particular fixed channel at a particular bandwidth. Okay, need not to use different sort of bandwidth to transmit n number of signals. With the help of single bandwidth, I can transmit the n number of signal with the help of FDM, with the help of this multiplexing technique. Once we have done with respect to frequency division multiplexing, now we will discuss with respect to the time division multiplexing. Here we are going to provide a particular signal for a particular time period, for a certain time period, and that time period is decided by a certain cases. How that particular time period is going to be identified. So first let me draw the block diagram for the TDM, then we will discuss its features, how it will operate, on what particular factors we need to give a stress so that the exact information can be extracted at the receiver end. Okay. So first, message components are provided to the low pass filters. This is called pre-aliased filters that we will discuss. Means it will restrict, if the low pass filter is given, that means it will restrict the signal to be a band limited signal. If a signal is provided, what is the bandwidth, up to what particular bandwidth we can consider, that need to be identified, and it is identified with respect to the filtering technique. Okay. So LPF, here I am providing M1 of t. Then this is one more LPF in which message component is M2 of t. Dot dot dot. There are n number of message component, m suffix n of t. And these all signals are provided to a, in frequency division multiplexing it is an adder. Here I will say it is called as a commutator. Done. And this commutator is having act as a switch, and that switch is rotating at a certain speed. That speed also we will see how to calculate those speeds. Okay. So this is called as a commutator. Commutator means it will combine the received signal, and that too we have to represent through a pulse amplitude modulator, PAM signal, because these all are continuous signal. We need to represent in a certain pulses for a fixed duration. Who will do this PAM loop, and how it is decided with the help of this particular sampler. Okay. So this PAM, then it is fed to a particular channel, and then at a receiver section it is called PAM demodulator. PAM demod means reconstruction of original signal, reconstruction of M1, M2, M3 from the sampled signal, from the pulse amplitude modulated signal. Last class we have discussed about the flat top sampling. Flat top sampling itself indicates that it is a pulse amplitude modulated signal. Next class after this TDM we are going to discuss about the pulse position modulation and pulse width modulation. Okay, very simple. That we will discuss later on. Only need to identify the PAM signal, change its position, it will become as a pulse position modulation. If you change the width of the position or width of the pulse, it will become as a pulse width modulation. And how we can recover all those things, that also some techniques are there that we will discuss in the next class. For the time being, we discuss on this TDM. Okay, it's a very interesting topic. So it is a PAM demodulation. After this PAM demodulation, it enters to the decommutator. In frequency division multiplexing, at the receiver end, we had again an adder form which will distribute the different sort of message component to the different signals, or different signals is provided to the different users, user 1, user 2, user 3, and it will identify. So here one more commutator is available, and this commutator is providing the signals to the different users. Okay, so different users. So here I will present 1 LPF, M1 I can extract here, then I can extract M2 here, and then I can extract the nth component, Mn of P. Okay, this is also rotating at the same speed. Now when you are doing this sort of TDM, your commutator, and this is your decommutator, it will act as demultiplexing. Here we are providing one signal, but it will split into n number of signals. So that is called decommutator. This is called as a commutator. And these decommutator and commutators are synchronized with each other. Okay, are synchronized. If it is not synchronized, we cannot expect that at this particular point M1 will be available, M2 will be available, or Mn will be available. We need to identify the synchronization, and this synchronization is done for the whole time division multiplexing process. Here what happens, m number of signals are given to the commutator, and this commutator provides the signal which is pulse amplitude modulated, and here the time slot wise it will create. So first time slot, second time slot, third time slot depend upon number of signals. Let us consider there are 3 individual signals are there. So first for 4 signals are there, if n is equals to, let us consider 4 independent signals are there, which need to be a time division multiplex. So what will happen? First is T1, second is T2, this is T3, this is T4. T1, T2, T3 means this is the time period allotted for the first message signal. This is the time period allotted for second message signal. Then this is the time period allotted for third message signal. And then it is 4. After this, again one more frame will continue with the T1, T2, T3, T4. Again it is a round robin process. Okay, so continuously this particular commutator will rotate, and this rotation depends upon the lowest frequency available in the given message content. It is a multi-tone signals, so we have to identify the minimum frequency through which this particular commutator will work. If the commutator is working at 2 omega, let us consider, your decommutator must also operate at 2 omega. If these two frequencies are not synchronized, you cannot recover the modulating signal. Okay, this is the basic block diagram for your time division multiplexing. Okay. So here few points I have written. You can explain these points by your own words. So these are the fundamental points what I have discussed with respect to this time division multiplexing. First, different time intervals are allocated for different signals. Yes, different time intervals are allocated to different signals. The combined signal is delivered to the common channel. Yes, the combined signal delivered to the common channel. Satisfied? Okay. Next, time of link divided into fixed size interval called as time slot or time slice. Yes. So, when this commutator or this particular switch is moving either anti-clockwise or clockwise in the same direction, your decommutator must also rotate. If this is moving in clockwise, this must also move in clockwise at the same rate. Okay, that is called as a synchronization. Then, next, when it is identifying position to position, the time period is created. For a certain time period, I am extracting one information. While combining this particular signal into a certain time slot, it will look like in this form of time slot, and this is called as a time slice. So time slice means each individual message components are given with the equal time interval. Okay, so that is called as our time slots. So time of link divided into fixed size interval called as time slot or time slice. Time slots are allocated to station in the round robin manner. Yes. After this what happens? After T1, T2, T3, T4 what will happen? Again T1, T2, T3, T4, because this commutator is rotating. If the commutator is rotating, n number of frames will be generated. This is one frame, this is one slice, or this is one time slot in which my informations are present. So these informations are transmitted toward the base station or transmitted toward the receiver station. So at this receiver station, these time slots are fed to the decommutator. It will extract, it will synchronize the time slot 1, message 1 time slot 2, message 2 time slot 3, message 3 time slot 4, message 4. So it will extract all this information and provide it to the receiver stations. Okay, this is the third point. Second, each station transmits data time allotted to it. Yes. So whenever this particular switch is placed to the station 1, that means message 1 is going to have for that particular time period. Similarly, when it is moved to the second one, second message signal is available. Moving to the nth signal is available. Then each station transmits data when time is allotted. Yes, each station transmits data when this switch is allocated to it. Who will decide? This commutator switch. So how this commutator and this decommutator will work? It will work at a rate of Fs greater than equals to 2 omega. Here Fs is not a Nyquist criteria. In Nyquist criteria what it is says, Fs greater than equals to 2 Fmax means what is the maximum frequency available in my modulating signal is multiplied and then the sampling frequency will come into picture. Here Fs indicates that it is a rate of a commutator and a rate of decommutator. And what is the relation? Fs greater than equals to 2 omega. Omega is the band limited signal. Here it is omega 1, here it is omega 2, here it is omega n. The band limited signal is having different bandwidth. Suppose one will have 1, 2, 3, 4, 5, 6 like that. How will identify the rate of this commutator? The rate of this commutator is identified by selecting the lower frequency available in the band limited signal. And you multiply 2 to it, you will get the commutator rate and you will get the decommutator. This is the most important factor. Many people what they do, they took the Nyquist sampling rate, means they multiply 2 with higher frequency and then they want to commutate. It is a wrong concept. Here we need to identify the lower frequency component. The lower frequency component multiplied to 2 and then you will get the commutator rate and decommutator rate. Okay. There are few other important points are there that I will jot it down now. Okay. So as you can see, there are two message signals. One is G1 of t, one is G2 of t. Okay, which is time division multiplex signal. So time division multiplex signal means, according to that block diagram, first the switch is provided with the message 1. So selecting that signal, pulse amplitude modulation is done. So the first sample is available. This one. This is first sample. This is the second sample for 1. I will write it like this. 2. Then third pulse 1. Then fourth pulse 1. Fifth pulse 1. Sixth pulse 1. Seventh pulse 1. Eighth pulse 1. Ninth pulse 1. So if I will join this dotted line, it follows the first modulating signal, that is G1 of t. Okay. Second, here I have considered two modulating signals. The second one is G2. Okay. So this G2 is when the switch is coming to that G2 position, it will identify that signal. Pulse amplitude modulation is done. So pulse amplitude modulation, first this is 2, second signal 1. Okay, this is second signal position 1, second signal second component, second signal third component, second signal fourth component, second signal fifth component. Similarly, this is second signal sixth component, second signal seventh component, then second signal 8 component, and second signal 9 component. So we are placing the PAM signal at an equi-space. You can see these all are equi-spaced. That means it is rotating was uniform. It is 2 omega. That commutator what I have written 2 into 2 omega, Fs is equals to 2 omega, where omega is the minimum bandwidth required or available in my band limited signal. So that frequency will be multiplied with 2, that will become as a sampling frequency for that commutator and decommutator. And this signal is called as a time division multiplex signal. So whenever these sort of signals are identified, it will generate n number of samples. The signaling rate we need to calculate. So certain fundamental terms are there through which we can identify the values. Okay. First, suppose if there are n message signal to be multiplexed. There are n number of message signals are there. 1, 2, 3, 4, dot 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 up to n. Ts is the sampling period, because it is a pulse amplitude modulation, means individual sampling frequency is going to come into picture. Okay. So Ts is the sampling period. And the distance between these two, this pulse and this pulse, this pulse and this pulse, this pulse, this pulse, this one and this one, that distance is called as Tx. Tx is called as time spacing between adjacent sample. So here you can see this point to this particular point is called as Tx. This particular point to this particular point is Tx. So that is the equi-spacing between adjacent sample. Now what is this Tx? Tx is nothing but sampling time period divided by n number of samples. So that is Ts divided by n. Okay. Now number of pulse per second. So number of pulse means 1 by Tx. So Tx is nothing but n by Ts. Ts it will go up, it will become n into Fs. This n into Fs is called as signaling rate, or it is also called as pulse per second. That is called signaling rate. In the exam they will ask what is the signaling rate. So signaling rate is R, small r, which is n into Fs. What is Fs? Twice into F max. Okay. So n into Fs, so it is n into 2F1. So here I have written. So here you can write n into Fs or 2n into Fm. Okay, because Fs is equals to twice Fm. Now if the rate is known, what will be my transmission bandwidth? The combined transmission bandwidth. The combined transmission bandwidth is signaling rate by 2. So signaling rate is n into fs divided by 2, where fs is nothing but n into 2fm. 2 will be cancelled out. You will get n into fm. So this is called as your transmission bandwidth. Okay, these are the fundamental terms which we are going to calculate for certain case studies. Okay, so this is the fundamental points. Few more fundamental points are there that I will discuss. Okay, so here you can see that the fundamental relations of a commutator and decommutator while designing. Okay, so these are the fundamental parameters. First, as you can see, what is the speed of commutator? The speed of commutator, as I have discussed, 2 omega. Okay, and we can write it is called as a revolution per second, RPS. Revolution per second. That is also called as a in terms of Hertz. So it is 2 omega. What is omega? Omega is the minimum bandwidth of a message signal. If there are 4 message signals, identify the minimum bandwidth, multiply 2 to it, it will become as a commutator speed. Okay. Second, speed of commutator sample per second. Sample means there are n number of samples are there. So speed of commutator with sample per second means first you need to identify the segments. How many number of segments are there? How many number of repetition of same signal is going to happen? So that is total number of segment into 2 omega means this commutator speed. So total number of segment into 2 omega, you will get your speed of commutator in sample per second. Okay. Third, what is the minimum bandwidth required? If there is only one signal, it is 2fs divided by 2, it is same as your 2fm. Okay. Similarly, if it is a minimum bandwidth required, if combined signal is there, half of summation of the Nyquist rate. For M1, fs1 is one Nyquist rate, for M2, fs2, for M3, fs3. What you have to do? You have to add fs1, fs2, fs3 divided by 2, you will get your minimum transmission bandwidth, and it is also called as bit rate. You can see minimum bit rate. Okay. Second, angle of separation of the corresponding segment. Suppose first message signal is present. I need to decide how many number of segments can be formed, and depend upon this the number of segment at what particular angle it can be placed while designing a particular commutator. Okay, we need to design it. So 360 degree is one revolution divided by the number of segment. Okay, suppose message 1, how many number of segment is required for message 1? For message 2, how many number of segment is required for message 2? You have to divide the 360 degree to get its original position. So that commutating or commutator will identify that particular position, that particular angle, and the segments can be formed. Okay. So n is the number of segments. Now, if there are different message signals are there, and those message signals are having different segments, now what are the adjacent angle between those segments? Message 1, message 2, message 3, message 4. So if I will consider first lot, what is the angle difference between those segments? So that is 360 divided by 360 degree divided by the total number of segments. M1 will have certain segment, M2 will have certain segment, M3 will have certain segment. Add total segments, and 360 divided by total, you will get the adjacent angles. Okay, this will help us to design the commutator process. Okay, so let us consider one case so that we can design the commutator principle. Okay, so here it is given a signal M1 of t is band limited to 3 kHz. So that means M1 of t having a bandwidth of 3 kHz, and 3 other signal M1, M2, M3, M4 of 1.5 kHz. Okay, these are transmitted with the help of this TDM technique. we need to set up a commutator scheme to realize the multiplexing with each signal sampled at Nyquist rate. We need to design that commutator. Okay. While designing that commutator, we have a certain table in which we can identify the number of segments, number of sampled signals, and what is the angle separation of that particular segment, and then we can calculate what is the adjacent angle will be there for different segments, for different message component. Okay, and then we need to find the speed of commutator in sample per second and the minimum transmission bandwidth. So minimum transmission bandwidth means he is indirectly asking about the bit rate. Okay, so these all things we need to calculate. So first of all, I need to form the table. So first is the message signal. Okay, and this, while solving this sort of questions, this table will help you to understand. First, message signal. How many message signal? M1, M2, M3 and M4. There are 4 message signals. Now, what is the Nyquist rate? First we will calculate for individual, because it will help you to calculate the transmission bandwidth. So for M1, as you can see, the bandwidth is 3 kHz. So what is the Nyquist rate? It will be 6 kHz. Okay, this is Fs, Nyquist rate. Similarly, M2 is having 1.5 kHz, so it will become as a 3 kHz. Similarly, M3 is 3 kHz and this is 3 kHz. Done. Now, third one is number of segment. We have to calculate. That is n. Okay, number of segments. Now, as you can see, here it is 6 kHz, 3 kHz, 3 kHz and 3 kHz. Now, how many number of segments do we require to combine all these signals? Now, the simple technique is to identify the number of segments is just see which is the higher frequency component and which is the lower frequency component. Divide those two. You will get the number of components, number of segments. So for this 6, if I will divide 6 by 3, that means we require 2 segments, or number of segments for 6 kHz or for message component is 2. And for this message signal M2, M3, M4, this all large segment is 1 and 1. It is simple, number of segments. Only need to identify maximum frequency and next you identify the minimum frequency. Divide these two, you will get your number of segments. So here for 6 is the maximum divided by the minimum, you will get 2 segments. Here it is maximum and minimum both are same. So it is 1, this is 1 and this is also 1. But in this case, if last one is 2 kHz, that means the minimum requirement is 2. So 6 divided by 2, 3 it will come. 3 divided by 2, it will become 1.5, near about 2. So round value you have to consider. So here number of segment is 2, 1, 1 and 1. Done. Now the segments are created. Next we need to identify the angle. Okay, angle of separation of segments. Okay, for segment. So how much it is? 360 degree divided by n. This is the relation we have seen. So now 360 degree for M1. How many times we can repeat? 2 times we can repeat. So that means what will be the angle separation? 360 divided by 2, it will become 180 degree. So that means the 2 message component of the same signal is available at a difference of 180 degree while designing the commutator I will show. Next, if it is 1, that means only one time it can be formed, that is 360. This is also 360 and this is also 360. Done. Now we need to represent what is the adjacent angle between the samples. So angle of separation between adjacent sample, okay. So how much it is? 360 degree divided by total number of samples. Total number of samples means 2 plus 1 3, 3 plus 1 4, 4 plus 1 5. So here it is 5. So how much it will be? It is 72 degree. Okay. So adjacent angle of the sample is 72 degree. Now I need to set up a commutator scheme. So this is my commutator. This is the switch. It is provided to the PAM and then it is delivered to channel. Okay. And this commutator is rotating with 2 omega. So what is the minimum frequency available in our message signal? Minimum frequency is 1.5 kilo. So that means the rotation is 2 into 1.5, that is 3 kilohertz. Or you can say it is 3000 revolution per second RPS. At this rate your commutator is rotating. Now I need to place message signal 1. So message signal is 1. How many times it repeats? 2 times, because 2 segments are there. And what is the angle separation? Angle separation is 180 degree. So let us consider this is my message 1 and this is my message 1. So it is 180 degree separation. Done. Next, message 2. So message 2 is how much degree? Only once it is repeating. So you can place here, and that message 2 is separated at an angle of how much? 72 degree. So let us consider this is message 2. Okay. This is message 3, 72 degree, and this is message 4, 72 degree. Done. So this is the quite simple representation. Only you need to identify the angles and the separation between them. So my switch will rotate in this particular direction, M1, M2, then M1, then M3, then M4. Because the M1 and M2 are 180 degree apart. And with respect to M1, other signals are also apart. At an adjacent signal is M2, M3, M4 is 72 degree and 72 degree. For this M1 and M2, you can see the adjacent angle is 72 degree. Here it is 72 degree. Okay. M1 and M4, how many are there? There are 3 signals are there. So 3 into 72. According to that, you have to place the M4. Similarly, M3. Similarly, M2. Okay. So this is the commutator design. Commutator design, or you can say it is called setup. Now, second question: find the speed of commutator. Here we have identified samples. Now we need to multiply the samples. So second is commutator speed in sample. So commutator speed in sample means how many number of samples are there? 5. What is the speed of commutator? 3000 revolution per second. So it is 15,000 RPS, or here you can say it is 15 kilohertz. Okay, this is the commutator speed. Then next, what is the transmission bandwidth? So minimum transmission bandwidth is summation of the Nyquist rate divided by 2. Okay, so what is the request rate? 6 kilohertz plus 3 and 3 and 3. So it is 3 into 3 is 9, 9 plus 6 is 15. So it is 15 divided by 2, 7.5 kilohertz. So this is the transmission bandwidth. That is the commutator speed, sample per second. This is sample per second. So whenever it becomes sample per second means total number of segments you have to multiply. So how many number of segments are there? 2 plus 3, 5. So 5 into 3000. 3000 what is the speed of commutator? Okay. So like this, or in place of this transmission bandwidth, the question may come what is the bit rate. So bit rate is nothing but the transmission bandwidth. And one more important thing, what is the signaling rate they may ask. So signaling rate is N into FM that you have to identify. Okay. So this is the small design for or the setup of commutator. Now one more question we will take with respect to this. Same question, I am changing the frequency component. M1 is 3.6 kilohertz and M2, M3, M4 is of 1.2 kilohertz. Done. Same thing we have to determine, but the values are different now. So first I need to calculate the request rate. So 3.6 into 2, how much it is? 7.2 kilohertz. Then 1.2 into 2 is 2.4 kilohertz. Similarly, this is 2.4 kilohertz. Similarly, this is 2.4 kilohertz. Done. Now, again number of segments we have to calculate. So how to calculate number of segments? Identify the maximum frequency divided by the minimum frequency. So if you divide this maximum by minimum, first one is 3 segments and rest all are 1, 1 and 1, because in this maximum is 2.4 and minimum is also 2.4 for this. For this maximum is 7.2 but minimum is what? 2.4. For this maximum is 2.4, minimum is also 2.4. So number of segments is this much. Now angle of separation of this segment, so 360 degree divided by 3, so it will come around 120 degree, because 3 segment means to complete the 3 I need 120 separation, so that it will become as a 360. Next, if it is 1, it will become as a 360 degree. It will become as a 360 degree. It will become as a 360 degree. Now what is the adjacent angle separation? 360 degree divided by 3 plus 1 4, 4 plus 1 5, 5 plus 1 6. So here I will put 6. So angle separation will be 60 degree. Now how I can set up the commutator? As we have done for the previous example, fed to the pan, then it is channel, and here the commutator is available and it is moving with a speed of 2W, where W is the minimum bandwidth available in the message counter. What is the minimum? Minimum bandwidth is 1.2. So 1.2 into 2 is 2.4, or you can say 2400 revolution per second. Okay. Now we need to place this message counter. Now first message, let us consider M3 of t. This is M3 of t, and this is M3 of T. All are separated at an angle of 120 degree. Then this is M1, sorry. M1 is separated at an angle of 121. And the adjacent angles are 360 degree, means there is only one repetition. So here you can put M2, here you can put M3, here you can put M4. And adjacent angle separation will become automatically 60 degree. Okay. So this is the commutator design. So according to this design, the further calculations are: first, commutator speed. So what is commutator speed? It is 2 omega. How much it is? 2400 revolution per second. Then commutator speed, sample per second. Sample per second. How much it is? It is number of segment we have to multiply. Number of segment is 6 into 2400. So that is 4400 revolution per second. 1400. Okay? 14400. This is one. Next, find the speed of commutator and the minimum transmission bandwidth. So minimum transmission bandwidth is equals to summation of Nyquist rate divided by 2. So now you have to add all this, 7.2 and 2.4. So if you add 7.4 plus 7.2, 2.4 into 3 whole divided by 2. So it is 7.2 plus, this is 12, 7.2 divided by 2, you will get 7.2 kilohertz. Okay, so this much is the minimum requirement for the transmission case or minimum transmission bandwidth. So that is 7.2. Like this, n number of questions may come. Sometimes they will give 3 signals, sometimes they will give 4 signals, sometimes they will give 5 signals. According to that, you have to design your commutator. And this commutator speed, sample per second, transmission bandwidth, angle separation of a segment, number of segment, angle separation between the adjacent sample. These are the fundamental questions comes in your TDM. Okay. So one question I am giving as a problem solving for you. Consider 3 message signals with message signal 1, which is band limited to 4 kilohertz. Okay, and the message signal 2 and 3 is band limited to 2 kilohertz. Okay, so this is your question. M1 is band limited to 4 kilohertz. M2 is band limited to 2 kilohertz, as well as M3 is band limited to 1 kilohertz. Okay, this is the first case. Same question, design your commutator, find out the table of this sampling Nyquist rate, find the speed of commutator, sample per second, minimum transmission bandwidth. This is first. Second one, if message is 6 kilohertz, M2, M3, M4 is all message component is having 2 kilohertz. Okay, you need to design for this also. You try this particular case, it will helpful for you to understand the table as well as to understand the parameters which help to determine the TDM properties. Okay. So for the time being, we will wind up this session. Next class we are going to discuss about PPM and PWM. Thank you.